Welcome to the third lecture for thermal physics. In this lecture we'll be looking at ideal gases a bit more, and we'll be looking at the theory of equipartition of energy. The lecture will be covering textbook sections 19.3 and 19.8. The most important points that we covered last lecture were you were introduced to the volume expansion formula. So you saw that the change in volume was equal to beta times the initial volume times the change in temperature. Now we saw that if you had the linear expansion coefficient, then beta is equivalent to 3 alpha. We also had to look at the ideal gas law, and we saw that there was two ways to write the ideal gas law. It can be written as PV is equal to nRT, where the little n here means the number of moles, and R is the gas constant 8.314. Alternatively, if we don't know the number of moles, rather we have just the number of molecules, so we have a lot less particles that we're considering, we can write the ideal gas equation as PV is equal to capital N, where capital N stands for the number of molecules, times Kb, which is Boltzmann's constant and is on your formula sheet, times T. In these equations, T is in kelvins, P is in Pascal, and V, the volume, is in meters cubed. Now we're going to be looking at the kinetic theory of gases. In kinetic theory, we make a number of assumptions. We assume that the number of molecules in the gas is large and that the average separation between them is large compared with their dimensions. This means they're not colliding too frequently and there's plenty of room for them to move about. We assume that the molecules obey Newton's laws of motion, but as a whole they move randomly. Now there's quite a lot contained within this assumption. Them moving randomly means they're just as likely to be moving in the positive x direction as the negative x direction. And they're just as likely to be moving in the y direction as the x direction. We'll be making use of this assumption in some of our derivations later. We assume that the molecules interact only by short-range forces during elastic collisions. So we're assuming that forces such as gravity, which act over a long range, are negligible. Gravity is negligible because it's so small, the mass of these particles is tiny, we can neglect it. We also assume that the molecules make elastic collisions with the walls, so they're not losing kinetic energy when they collide with the walls of the container. And finally, we make the assumption that the gas is a pure substance, all the molecules are identical. So what we're going to do now is we're going to derive an expression for the relationship between temperature and molecular kinetic energy. This will actually provide us with a definition of what temperature is for a gas. The derivation's long, you do not need to be able to reproduce it, but you do need to understand how we get from one step to the next. For this derivation, we're going to assume that we have a cube with a volume d cubed. Each of the sides has a length d. Inside this cube, we're going to put capital N molecules of an ideal gas, and each of these molecules is going to have a mass m0. Now, we've shown previously that the force is equal to the mass of the particle times the change in velocity over the time for the collision. So we showed that this was equal to 2m0 vfx over the time for the collision. Now, for the kinetic theory of gases, we're interested in the average force because we have a lot of molecules here. So if we want the average force for one molecule, instead of dividing by the time for the collision, we're going to be dividing by the time between collisions. For one molecule, it'll collide with the wall and there'll be a large force. This is 0. And then it'll travel from one wall to this other wall and back, so it's travelled a distance that's distance d and it's travelled it twice, so total distance. It will then hit the wall again and collide again, and so this is the force on the one wall. We can see that this time between the collisions is the distance over the velocity. So that's 2d over vxi. And if we want the average force on the wall, we want to spread this force out over this time. So we're going to replace that t for the collisions with the t between collisions, which is the 2d on vxi. So delta t is equal to 2d on the initial velocity in the x direction. So the average force acting on the wall is 2m0 vxi over that time between collisions. So replace this with the 2d on vxi, and we end up with vxi squared. And so the 2's will cancel out, and we're left with the force is equal to m0 vxi squared on d. Now this was the force for one molecule, but inside our box we have n molecules, so we're going to have to add up the contribution of each of these molecules. Now m0 and d is the same for all molecules, so that's a common factor. So we can pull the m0 and the d out the front. We then need to add up the velocity squared of each of these particles in the x direction. So the average velocity squared in the x direction is given by to take the average of anything, we just need to sum up all the values and then divide by the total number of particles or the number of values we're adding. So this is the expression for the average velocity squared in the x direction. The line over the top means average. So we can use this expression to write our total force on the walls as F is equal to m0 on d n vx squared, taking the average there. Now, so far we've only looked at the x component, but we can say that the total velocity squared is equal to the total velocity in the x direction squared plus the total velocity in the y direction squared plus the total velocity in the z direction squared. That's just Pythagoras' theorem. The average values are related by the same formula. If we take the average of each of these values, it will be the same. So the average velocity squared is equal to the average velocity in the x direction squared plus the average velocity in the y direction squared plus the average velocity in the z direction squared. When we were introducing kinetic theory, we said that we would make the assumption that the particles were moving randomly, which means they're just as likely to be moving in the x, y, and z direction, which means vx squared should be equal to vy squared and also to vz squared. So what we can do is we can replace the vy squared and the vz squared in that equation down the bottom of the last slide with vx squared. So we're adding 3 lots of vx squared. So the average velocity squared is equal to 3 times the average velocity in the x direction squared. This is useful because in our formula we had the average velocity in the x direction, so we should now be able to replace that with just the average velocity squared. So we're replacing vx squared with v squared on 3, so that's where this 3 comes from. This 3 is effectively coming about because of the 3 dimensions, because we've got an x, a y, and a z dimension. So it's 1/3 n m0 v squared on d. Okay, now we can calculate the pressure. We know that pressure is equal to force over area, and we were imagining a cube, so the area of the cube is d squared. So we've got 1/3 n m0 v squared over d cubed, which is 1/3 n on v m0 v squared. We're taking the average of the v squared. Now we can relate this to the kinetic energy of molecules. Kinetic energy is given by a half mv squared, so we need to put a factor of a half in here. If we want to write a half there, we'll need to put a 2 up here so that we're not changing the total expression. So we can write P is equal to 2/3 n on v times a half m0 v squared, and this term here is the average kinetic energy of the molecule. This is also Boyle's law because we've now got P is inversely proportional to V. So we've derived that from the microscopic properties, and we've got our constant here. The constant includes the kinetic energy of the gas. Now what we were trying to do was to get a relationship between temperature. So to do that, we can relate this equation that we've just derived with the ideal gas law. And so equating these, we can see that nkBT is going to be 2/3 N times 1/2 m0 V squared. Then the n's will cancel out, and rearranging to get T, we've finally got what we wanted. 2/3 kB times 1/2 m0 V squared, where this is the kinetic energy of the gas. So this is actually our definition for temperature of a gas. Temperature of a gas is given by 2/3 kB times the average kinetic energy of the particles that make up the gas. Okay, so a question. The root mean squared of an oxygen molecule, remember oxygen's one of those diatomic ones, so it's O2, in a container of oxygen gas is 625 meters per second. What is the temperature of the gas? Okay, but first, before we answer this, we're going to have a quick look at what we actually mean by root mean squared. So root mean squared is just the square root of the average velocity squared. So the average velocity of the gas is 0 because it's just as likely to be moving in the x direction as the negative x direction. So in the x or the y or the z direction, the average velocity is 0. So the average velocity is 0. So we need to square the velocity and then take the average. Okay, if we were to find the RMS speed of these particles, let's assume these are in meters per second in the I direction, then what we need to do is square each of these numbers and add them together, divide by the number of numbers that there are, and then take the square root. Okay, so what we do is 1 squared, which is 1, plus 2 squared, which is 4, plus 4 squared, which is 16, plus minus 3 squared, which gives us 9. And now there's 1, 2, 3, 4 values there, so we divide by 4. Then we take the square root. When you do that on the calculator, you get 2.74. So the RMS velocity for these values is 2.74. Okay, let's now go back to this question where we've got the oxygen molecule and its root mean squared velocity is 625 meters per second, and we're asked to find the temperature. Okay, so we've been asked to find the temperature, and we're told that the root mean squared velocity is equal to 625. So we can say that the average velocity squared, which is the square of the root mean squared velocity, 625 squared. Solving that on the calculator, we end up with 390,625. We'll keep all our significant figures for now. Now, temperature is equal to 2/3 kB times the average kinetic energy. So we've got this velocity squared. kB is just a constant that we can look up. What we need to work out is the mass of an oxygen molecule. So the mass of oxygen, if we look it up on the periodic table, oxygen has an atomic mass of 16. So to get the molar mass, it's a diatomic molecule, so we need to times this by 2. And this is grams per mole. So let's put that into kilograms. We times it by 10 to the minus 3. And then we need the mass of a single particle, not of 1 mole of particles. So we divide it by Avogadro's number, 6.022 times 10 to the 23. When you do that on the calculator, you end up with 5.3138 times 10 to the minus 26 kilograms. Okay, so now we're ready to substitute everything in here. The temperature is equal to 2/3 over kB, so that's 1.381 times 10 to the minus 23 times 1/2 times this number, 5.318 times 10 to the minus 26. Times our velocity squared, which is this number up here. Okay, we solve that on the calculator and we end up with 501 kelvins. Okay, and 501 kelvins looks like a reasonable answer. It's of the same order of magnitude as room temperature, so that's what we'd expect. So quickly, just a question. One container is filled with helium gas and another with argon gas. Both containers are at the same temperature. Which molecules have the higher RMS speed? Explain. So if they're at the same temperature, we know that they have the same average kinetic energy. Now, since the helium atoms have a much lower mass than the argon atoms, the helium atoms must be moving much more quickly to have the same kinetic energy. So the helium atoms have the higher RMS speed. Okay, now we're going to get onto a very important concept, degrees of freedom. Every kind of molecule has a certain number, F, of degrees of freedom, which are independent ways in which the molecule can store energy. So what ways can molecules store energy? Well, they can generally store it as kinetic energy. You saw in mechanics that we had translational kinetic energy and also rotational kinetic energy. Molecules are the same. They have translational kinetic energy, some can have rotational kinetic energy, and some can even have vibrational kinetic energy. Let's look at a few specific cases. And monotonic, so this is just a single atom. Helium, argon, or the noble gases are found in this form. A helium atom can move in 3 directions. It can move in the X direction, the Y direction, and the Z direction. So there's 3 ways it can store kinetic energy. So it's got 3 translational degrees of freedom. Now, a helium atom can also rotate. Classically, we'd say that it would be able to have rotational kinetic energy. However, it's not, you can't tell one point on the surface of a helium atom apart from another. So if you're looking at it, you can't actually see it rotating. So quantum mechanically, it turns out that it doesn't actually have any way of storing energy rotationally. So a monotonic atom has 3 translational degrees of freedom and no rotational degrees of freedom. So that means it has 3 degrees of freedom, and the total energy it can store is 3/2 kBt, which was the same as the average translational kinetic energy. Now let's consider a diatomic molecule, which is 2 atoms stuck together, e.g. O2, H2. So the diatomic molecule can also move in the X, Y, and Z direction. So there's 3 ways for it to store kinetic energy translationally. Now it can rotate about 3 axes. It can rotate in the XY plane, the YZ plane, and the ZX plane. And we can see it rotating in 2 of these planes. But if it's spinning about the axis between the molecules, so this is spinning and this is spinning around and around on this axis, then we can't actually see it rotating. So it cannot store rotational energy in that way. A diatomic atom can also vibrate. These can move relative to each other. Now there's 2 vibrational degrees of energy. We can store the energy as potential energy by setting how far apart these atoms are initially, and also the kinetic energy by how fast they're moving relative to each other. So there's 2 vibrational degrees of energy. So the total number of degrees of freedom for a diatomic atom is the 3 plus the 2 plus the 2, which gives us 7. So the total energy that a diatomic molecule can store is 7/2 kBt. Now, it's important to note that at low temperatures, the molecule doesn't actually have enough energy to start rotating or vibrating. So below around about 100 kelvins, the molecule actually only has 3 degrees of freedom, just the translational degrees of freedom. Above 100 degrees Kelvin and below 1000 degrees Kelvin, it has enough energy to rotate, but not to vibrate. So for this region, we end up with 5 degrees of freedom, and then above 1000 kelvins it has enough energy to start vibrating, and so that's when we end up with the 7 degrees of freedom. So when you're answering a question about diatomic molecules, you do actually have to look at what the temperature is and take that into account. There's also polyatomic atoms, polyatomic molecules that are made up of lots of atoms. So for example, methane. Now all these molecules have 3 translational degrees of freedom because there's 3 directions that they can move in. They can generally rotate about the 3 axes. Obviously this is going to depend a bit on the geometry of the particle, of the molecule. So generally they have 3 rotational degrees of freedom, but you will sometimes have one that only has 2. They also have many different vibrational degrees of freedom. So you wouldn't be expected to work out how many vibrational degrees of freedom or rotational degrees of freedom a polyatomic molecule has. Below 100 degrees Kelvin, polyatomic atoms only have 3 degrees of freedom. Between 100 kelvins and 1000 kelvins, they also have the rotational degrees of freedom. So they generally have 6 degrees of freedom at that time. And then above 1000 Kelvin, they start vibrating as well. So you need to add in however many degrees of freedom there are for the vibrations for that particular molecule. However, you won't be asked questions about molecules which are this complicated. So this brings us to the theorem of equipartition of energy. The theorem of equipartition of energy says that each degree of freedom contributes 1/2 kBt to the total energy of the system, where possible degrees of freedom are those associated with translation, rotation, and vibration of molecules. So the total energy of a gas is 1/2 Fn kBt. So for a monotonic gas, that's equal to 3 on 2 nkBt, as F is 3 for a monotonic gas. For a diatomic gas, it would depend on the temperature. So here's a question to think about. 2 containers hold an ideal gas at the same temperature and pressure. Both containers hold the same type of gas, but container B has twice the volume of container A. What is the average translational kinetic energy per molecule in container B? Well, to answer part 1, we know that the translational kinetic energy is just proportional to the temperature of the gas. So as these 2 gases are at the same temperature, they must have the same translational kinetic energy. And so the answer to part 1 is B, the same as that of container A. Part 2 says describe the internal energy of the gas in container B. Well, the internal energy we saw on the previous slide is equal to 1/2 Fn kBt. So there's an N in there, the number of molecules. As these gases are the same at the same temperature, same pressure, if volume B is twice that of the volume A, then container B must have twice as many molecules in it as container A. So if it has twice as many molecules, then it's going to have twice the internal energy stored. Okay, part 3, we now imagine that these gases are of different types, meaning they could have different degrees of freedom. If we were to answer 1 with different gases, the translational kinetic energy is only dependent upon the temperature. So since they are at the same temperature, it will be the same. So the same as that of container A. And part 2, describe the internal energy of the gas in container B. Okay, now if these are different gases, we don't know how the degrees of freedom compare. So even if there are twice as many molecules in container B, it's possible that the gas in container A could have twice the number of degrees of freedom. So in this case, we don't actually have enough information to answer this question. So part D is the correct answer for if the gases are different for part 2. So a question. A 2 mole sample of oxygen gas is confined to a 5-litre vessel at a pressure of 8 atmospheres. Find the average translational kinetic energy of the oxygen molecules under these conditions. So in order to answer this question, we're going to need to use that the average kinetic energy, which is given by this formula, is equal to 3/2 kBt. And so in order to calculate this, we need to know what the temperature is. Now, in order to calculate T, we can use the ideal gas law. So use ideal gas law. So the ideal gas law tells us that PV is equal to nRT. So we can rearrange this to write T is equal to PV on NR. And we're actually given all of these values, so we just need to substitute them in. Now, P, we're given as 8 atmospheres. So in this equation, we need it in Pascal. So that's 8 times 1.01 times 10 to the 5. That will convert this 8 from atmospheres to pascals. And now we're given that the volume is 5 litres, and we need the volume in meters cubed. So that's 5 times 10 to the minus 3. That's because there's 1,000 litres in a metre cubed. And then we need to divide by N, which we were told is 2, and R is the gas constant, 8.314. So now we just need to calculate that on the calculator, and we end up with a temperature of 242.96 kelvins. And now we can just substitute it back into this equation here. So we've got our average kinetic energy is equal to 3 over 2 times Kb, which is 1.381 times 10 to the minus 23 times 242.96, and solving that on the calculator we get 5.03 times 10 to the minus 21 joules, which is a very small number, but then this is talking about a single oxygen molecule which has a very low mass, so we would expect it to be very small. Another question. A. How many atoms of helium gas fill a spherical balloon of diameter 30 centimeters at 20 degrees C and 1 atmosphere? B. What is the average kinetic energy of the helium atoms? And then C. What is the RMS speed of the helium atoms? Okay, so to answer part A, we need to calculate how many moles are in that balloon. So we can just use the ideal gas law. PV is equal to nRT, and we're trying to find N. So N is equal to PV over RT. And so let's start by calculating the volume. This is a spherical balloon, so the volume is given by 4/3 pi r cubed. And so this is 4/3 times pi times, now we were told that the diameter was 30 centimeters. So the radius is 15 centimeters, or 0.150 meters. And so we cube that, and we get a volume of 0.1414137 meters cubed. And now we can just substitute into this equation for N. So N is equal to P, which was 1 atmosphere, 1.01 times 10 to the 5 pascals, times 0.014137 over R, which is 8.314. And then we were told this was 20 degrees C. This needs to be in kelvins, so that's 20 plus 273.15 to convert from Celsius to kelvins. And solving this, we end up with 0.586 moles. Now for part B, we need to find the average kinetic energy, and we know that that's given by a half mv squared, which is equal to 3 over 2 kBt. And so this is equal to 3 over 2 times 1.381 times 10 to the minus 23 times T in kelvin, so 20 plus 273.15, and this is equal to 6.07 times 10 to the minus 21 joules. Now part C asks, well, what's the RMS velocity of these helium atoms? So in order to do that, we need to use that V, the average velocity squared, is equal to the RMS speed squared. And so from up here, we can see that VRMS squared will be 3 over 2 kBt times 2 and divided by m. So we're going to need to know the mass of helium. And so we can look it up on the periodic table, and this is 4.002602 atomic mass units. We need to get it into kilograms to substitute it in here. So in order to do that, we've got 4.002602. Now this is grams per mole. So we times it by 10 to the minus 3 to make it into kilograms, and then we need to divide by Avogadro's number to get the mass of one molecule rather than Avogadro's number of molecules. And so that is equal to 6.6466 times 10 to the minus 27 kilograms. And so we can now put this number into the equation here. And so we've got VRMS squared is equal to 3 over 2 kBt, which is the 6.07 times 10 to the minus 21 that we calculated in part B, times 2 divided by 6.6466 times 10 to the minus 27. This is equal to 1,826,488. And so to get the root mean squared, we take the square root of that, and that is equal to 1,351 meters per second. So fairly fast, and because that's so fast, that's why so much helium's escaped the Earth's atmosphere. Helium, because it's so light, travels very quickly, and so it's more likely to exceed the escape velocity and escape from the Earth's atmosphere. So next lecture we're going to be looking at work done on gases. So it's very important that everybody remembers about work from mechanics. So here's a bit of a revision question. A group of students is doing an experiment to measure the drag force acting on raindrops of various sizes. A particular drop has a mass of 3.4 plus or minus 0.1 times 10 to the minus 5 kilograms. It falls a distance of 100 plus or minus 1 meters at constant speed under the influence of gravity and air resistance. What is the work done on the raindrop? A, by the gravitational force, and B, by air resistance. So in this problem we need to calculate the work. Work is equal to the force times the distance, as long as these are acting in the same direction. So in this case, with our raindrop, we've got the weight force acting downwards, we've got the air resistance force acting upwards. Now, because this raindrop is falling down with a constant velocity, we know that these two must have the same magnitude. So the air resistance force is equal to the weight force. And the R, the raindrop is travelling downwards, and so that is the direction of this R vector. So in part A, we need to calculate the amount of work done by the gravitational force. So in this case, the gravitational force and the displacement are in exactly the same direction, so we're going to get a positive answer. So in other words, the gravitational force is doing work on the raindrop, which means it's causing the raindrop to gain energy. So this is equal to F, which is the weight force, mg, times R, which in this case is the distance fallen. Now in their question, we're told that the mass of the raindrop is equal to 3.4 plus or minus 0.1 times 10 to the 5 kilograms, to the minus 5 kilograms, sorry, and we know that the distance it falls is equal to 100 plus or minus 1 meters. So we're actually going to need to take into account our uncertainties as well. Okay, so we just need to substitute these numbers into this formula. So we've got 3.4 times 10 to the minus 5 times g, which is 9.8, times d, which is the 100 meters. And solving that on the calculator, we get 0.03332 joules. Now let's consider the uncertainties before we give this to the right number of significant figures. So from the lab, you know that the uncertainty in the work over the work, because it just comes from multiplying these quantities, which are completely independent, this measurement and this measurement will be made completely independently of each other, and there is no uncertainty in G. We know that that's exactly 9.8, so this is equal to the square root of the uncertainty in the mass over the mass squared plus the uncertainty in the distance over the distance squared. We add them in quadrature, so this is equal to 0.1 over 3.4 squared plus 1 over 100 squared, and this is equal to 0.031. And so in order to get the absolute uncertainty in the work, we just need to multiply this work by this number here, and this gives us that the work is equal to 0.033 plus or minus 0.031. 0.001 joules. And it's a positive answer because the gravitational force is doing work on the raindrop. Now, for part B, we're asked to calculate the work done by the air resistance force. Now, in this case, the air resistance and the displacement have opposite directions, and so we're going to get a negative answer. So this is going to be exactly the same, but with a negative answer. So we'll have work is equal to minus 0.033 plus or minus 0.001 joules.